You know, we're surrounded by numbers, but we actually use them in two totally different ways. Sometimes close enough is, well, it's good enough. But other times, it has to be absolutely perfect. So, what's the hidden math that decides when a rough guess works and when every single detail matters? Let's dive in and find out.
Okay, so you're scrolling through the news, and you see a headline like this. A huge, devastating number from a report about, say, recent floods. That number is there for one reason. To hit you with the scale of the tragedy, right? The sheer size of it all. But let me ask you something. When you read that, do you honestly picture exactly 80,000 people? Not 80,001? Not 79,999? Yeah, probably not. And you know what? If you're a little bit skeptical of that perfectly round number, you should be. You're right on the money.
That's because what we're looking at is a classic example of something called estimation. It's basically a math tool we pull out when the big picture is way more important than the nitty-gritty details. It's for when close enough is all you need to get the story across.
So the headline gives us this nice, clean, easy-to-digest number, 80,000. But let's be real, the reality on the ground is never that neat, is it? It's always messy. The actual precise number could have been something like 76,839. Or maybe it was 84,372.
And that's the trade-off, isn't it? Estimation is super powerful. I mean, it lets our brains wrap around these enormous events. But to give us that clean picture, it has to kind of smooth over the messy, super specific details of what actually happened. Which, of course, brings us to the flip side. When is close enough absolutely not good enough? When do we have to throw estimation out the window and demand absolute pinpoint precision?
Well, how about something we all deal with? A shopping bill. Think about it. There is zero room for close enough here. Every single item, down to the last rupee, has to be perfectly accounted for.
So let's break this down, because when you're looking at a bill, precision isn't just a nice little feature, it's literally the whole point.
See? A bill is built on these layers of absolute precision. First, you've got the individual items purchased, each one listed out. Then you've got the quantity, exactly how many of each thing you bought. Next comes the rate, the precise cost for one of those items. Each step is like a link in a chain, and it has to be perfect, leading to one final unchangeable number.
1,093 rupees. Not around 1,000. Nope, not somewhere in the ballpark of 1,100. It is exactly 1,093.00. The shopkeeper expects that exact amount, and you expect to pay not a single paisa more or less. This is where perfect accuracy isn't just an idea, it's a requirement.
And right there, that's the whole idea. You've got these two different ways of using numbers. One is for getting a quick grasp of the big picture, and the other is for perfect must-be-right accuracy. And they're not enemies. They're just different tools in our math toolkit for totally different jobs.
Okay, so what happens if we take this exact same idea, this whole close enough versus pinpoint perfect thing, and apply it to shapes instead of numbers? Let's jump into a new dimension, moving from flat numbers on a page to the 3D world all around us. So here's the puzzle. How do you take a real, physical 3D object, like a box, and draw it accurately on a completely flat 2D piece of paper? I mean, how do you possibly capture its height, its width, and its depth all at the same time? Well, the solution is actually pretty similar to the estimation we were just talking about. Since you can't really show the entire 3D object at once on a flat surface, you do the next best thing. You use a kind of approximation. You show a bunch of specific, simplified 2D views instead. And in fields like engineering and architecture, this is all standardized. They have three main views they rely on. You've got the front view, which they also call the elevation. Then there's the side view. And finally, the top view, which is known as the plan. All right, first up, we have the elevation. That's just the fancy word for the front view. Imagine you're standing right on the sidewalk, looking straight at the house. This drawing shows you exactly what you'd see: the front door, the windows, the shape of the roof from that one single angle. It's one very precise piece of a much bigger puzzle.
Okay, now let's walk around to the side of the house. We're looking at the side view. And look what's changed. The front door, it's gone. Now we see a totally different wall, maybe a different window. This view gives us a whole new piece of precise information. It shows us how deep the building is.
And last but not least, we have the plan. This is the top-down view. It's kind of like you're a giant floating above the house and you've lifted the roof off to peek inside. This one is so important because it shows the layout, how thick the walls are, and how all the rooms connect. And here's the really cool part, the beautiful paradox of it all. You take these 3 separate, simple 2D approximations. On their own, none of them tell the whole story. But when an engineer puts them all together, bam! They have every single precise detail they need to go out and build the complete, perfect 3D house in the real world.
Which brings us right back to where we started. It doesn't matter if we're rounding off a huge number for a news headline to show scale, or if we're drawing a perfectly precise blueprint to build a skyscraper. We're using the exact same fundamental language, math, to understand and to literally build the world around us.
It's a language that can handle both sweeping, big-picture guesses and tiny, painstaking details. It really makes you think, doesn't it? What other hidden math is out there, silently and perfectly, running your world right at this very moment?